All right, to start off with, we're going to talk about are mutually exclusive. So what does it mean for two events to be mutually exclusive of each other?
Two events can never happen at the same time.
They can't happen at the same time. So it's impossible to flip a coin, it land on heads and tails. It's not going to happen, so we don't have to worry about that. So if we want to find whether these two events are mutually exclusive, we have these two events. So we have picking a random letter from the alphabet and having that letter be a vowel, or picking a random letter from the alphabet and that letter being a letter from the word geometry. So are these events mutually exclusive? No, they are not mutually exclusive because they can happen at the same time. We have two vowels in geometry, technically three, but two distinct vowels, without counting Y. And so E and O would be our two possibilities that you can get that would be probability of both of them at the same time. So this is not mutually exclusive. Good. That's one of our big things that show up. So if we did want to find what the probability of both of these, if we did want to find what the probability of picking a random vowel and picking a letter from the word geometry, what would that probability be?
Like 5 out of 26 for like the vowels, and what, like 2 out of 26? But then like you have to minus the overlap thing.
So I think you're thinking of probability of A or B.
Oh.
So you're thinking of probability of being either event. We want the probability of both of these events at the same time. So the probability of this and that both occurring at the exact same time. So how many vowels do I have in geometry? 2. Or 2 distinct vowels. Like technically E shows up twice, but the probability of getting E is still the same, even though there's 2 probabilities. It doesn't matter how many times E shows up in this word. Probability of getting E is still 1/6, or 1 out of 26. And so 2 out of 26 is our probability of getting an E or an O. And so the total would be a 0.08. Now we're thinking about the probability of getting an E or a vowel or a letter from the geometry. Once again, we talked about these. Instead of writing and, you might see that upside down U sign, that intersection. Or instead of writing or, you might see our capital U, our intersection. And those are just different ways of writing it that we just want to be familiar with. But now I want to talk about the probability of getting a vowel or a letter from the word geometry. How many vowels do we have?
This one you would just do like with like 2 different ones, and then you just do the
Yeah.
I think you're on the right track. So we want to find what's the probability of getting a vowel plus the probability of getting a word or a letter from the word geometry minus the overlap from the two, vowel and geometry at the same time. So vowels, I have 5 out of 26, my vowels. E, I, O, U. Geometry, I have 7 distinct letters, even though there's technically 8 letters in geometry. E shows up twice, and so the probability of getting an E doesn't change no matter how many times it shows up. I could have 16 E's in here, and it'd still be 7 out of 26. And so 7 out of 26 is my probability of getting a letter from the word geometry. And then the probability of getting both of them at the same time, we already said was 2 out of 26. Because that is E and O, where there's only 2 letters that meet both requirements. And because E is counted in the vowels and geometry, and O is counted in the vowels and geometry, we have to make sure to subtract by that so we don't count it twice. So 5 plus 7 minus 2 is 10 out of 26. We can then divide that to get 0.38. Are we good with this? Okay. So that was sort of this. That was the stuff we talked about mainly on Wednesday of last week. We talked about those conditional probabilities, or those compound probabilities, the ands and the or statements, and then the mutually exclusive. We'll also talk about independent events. What does it mean for 2 events to be independent? They don't affect each other. Me flipping my coin over here isn't affecting whatever I roll on my dice. What was that? Yeah, Gabe's doing a backflip doesn't affect my probability of looking outside and seeing a red car or whatever it was. All right. We also looked at frequency tables last week, I'm sorry. And so we have that table. So this was one of the exact same tables we saw last week. So it has male and female students, and then students who are involved in activities and students who aren't involved in activities. So what is our probability that a randomly chosen student is female? Based off that table. 259 out of 516. So we have 259 total females out of 516 total students. 259 out of 516, and should be just roughly, I think it's like just greater than half of the population was females. Now, how many students were a male that was also involved in a school activity? So we have 112 total students, or male students involved in activities out of our 516 total students. And so the probability of being a male and involved in an activity is the 112 over the 516. Were you thinking of the... Yeah, we're going to talk about that one next, where we have to like narrow it down. So good. So 112 over 516, I think, is 0.22. And that's our probability of meeting both those requirements just randomly out of all of the students. And then we also talked about those conditional probabilities last week. And that's where they give us that extra little piece of information to help us narrow down our search, or help us, we're looking at a certain group instead of the entire group. So we have, what is the probability that a chosen student is female given that the student is not involved in any activity? So now we have that given extra piece of information where we're narrowing down our results. Because we just want to look at those students who are not involved in any sort of activity. Is that okay? So how many female students do we have? 120. So 120 out of 256. And once again, the way we wrote that was, it would be the probability of being a female given that they're not involved. And so our probability of being a female was, and not involved, was the 120 out of our total number of students who were involved, or 265, I'm sorry. I'm always switching around my numbers. And we found that result to be 0.45. Are we okay with this? And this is what we did last week, especially with the Titanic problem that we were doing. So we had the Titanic and we were looking at, okay, what was my probability of surviving given I was a first-class passenger? What was my probability of being a third-class passenger given I had survived, or something like that? And those were off. So we can find these conditional probabilities by narrowing down those results. But now we want to take it one step farther. So we've only been able to use these with our frequency tables. We want to see, okay, how can I find a conditional probability if I'm not given a table like this? If I'm just given, what is like the minimum pieces of information I need in order to solve these questions without having a table? So let's sort of break down where we're taking these numbers from. What does that 120 stand for? What does that represent?
The females not involved in activities.
Females not involved. So we found, okay, how many females? So this is really, because it's females not involved, it's females and not involved. It's one of those and statements that overlap the two. What does the 265 represent?
How many total male and female?
So that's total number of students not involved. So just any not involved. So to find this conditional probability, what we did, we found what was that overlap of the two statements? What was the overlap of those two events? And then we divided it by that given event. So we divided it by our given information that we're not involved, and we looked at what was the overlap of those two, that and criteria. So we can take this and we can expand it for any conditional probability. So the conditional probability of some event B, after you're given that you have event A, or given whatever event A is the probability of both the and statement of them divided by the probability of that given event. And this works for any situation. As long as you know those two things, we can find any conditional probability of those two. Sometimes it might give us a little extra information, like the frequency tables had a little extra information on them. Sometimes they'll just give you enough information to solve. But anytime the conditional probability, we can use that B, or the intersection of the two, A and B at the same time, divided by just that probability of it. So if you're going to remember anything from today, this is like the same thing. Once again, we saw it using, it was the probability of a female given that they weren't involved in the activities. We looked at the probability of both, female and not involved, divided by that probability of given piece. I know some students like to think about it as if you see that given information, you take both of them and put them together, find what's both of them together on the top, and then you think about it as like dividing by that second piece. And so always whatever is the given, that second part is always what's going to go in the denominator. And then both of them will always go. Are we okay with this? Now something we'll look at later on a problem is if you flip these around, if it was a probability of not being involved given that it's female, it's not going to be the same answer. The only time it will possibly ever be the same is if the probability of being a female and the probability of not being involved is 50-50. But if we flip them around, they will actually be different. We'll look at an example later on of how it's actually, if we flip them around, how it actually changes. But we're just going to practice working through a couple problems with these, practice figuring out what those pieces of information and then using them to solve. All right. So let's say a study is designed to test the effectiveness of a new drug. So people are trying to figure out, okay, is this drug actually doing anything? Is it actually working, or is it not very good? Half of the volunteers that are volunteering to take this drug receive the drug. The other half would just take a fake pill. So they take a pill that has no sort of medication. Yeah, it's like a placebo effect. And so we want to figure out what is the probability that if a volunteer receives the drug and the probability that a volunteer is receiving the drug and getting well is 45%. We want to figure out what is the probability that if someone is getting well, given that they receive the drug. So once again, that given word is supposed to tip us off that we have a conditional probability. So it's the probability that they receive the drug, it's the probability that they're getting well, given that they took the drug. So what we just saw on that last slide was it's the probability of both of them divided by the probability of that given event. So the probability of getting well and taking the drug, all divided by the probability of just taking the drug. So how likely is it for me to get well and receive the drug? 45%. We said the probability of a volunteer receiving the drug and getting well, that and statement is 45%. So 0.45 is going to be our numerator. Then I have to figure out what is my probability of actually just receiving the drug, Joe?
Right now.
How many of our volunteers receive the drug?
Yeah, half, so good.
Half of them. So 50% my probability of receiving the drug. So 45 out of 50 was my probability of receiving or getting well after receiving the drug. If we divide that, it should be 0.9. So 90% of the people who took this drug got better. So I'd say seems fairly effective. Seems like it's working. Are we okay with where we're pulling these numbers from, where we came up with these results? Okay. Same situation, same sort of scenario. if a volunteer was given the pill with no medication, take out that placebo one, they had a 20% chance of or 20% probability of improving their health. So what was the conditional probability that of a volunteer's health improving given that they had no medication, that they received no medication, they just got that placebo? Probability of getting well given they did not receive the drug. So once again, when we break this down, we're always looking for two things. The probability of both of them occurring divided by the probability of them given. The probability of getting well given that they did not receive the drug, or sorry, not receiving the drug, I'm sorry, divided by the probability of just not receiving the drug.
So it's always over the second.
It's always over that second given piece of information.
Which is 12.
So what's my probability of getting well and not receiving the drug? 20%. Okay, so that's our numerator. Out of what? How many of us did not receive the drug? Or how many volunteers, I'm sorry? So it's still going to be out of the 50. So even though the total is out of 100, it's still going to be, if we just wanted to figure out what was the probability of receiving the drug and not getting well, if we didn't have that given an extra piece of information, it would have been out of 100 or out of 1. But just because we're looking for that specific piece. And so if we divide that, this should be 0.4. So 40% of the people who did not receive the drug got well from that placebo effect. They thought they were getting the drug, so they thought that they were going to get better, and so their body just made it better. Which is crazy that your mind can do that, but that's a wonderful story. Are we okay with this? And where we're pulling these numbers from?
Was this like all different?
We're just gonna keep reviewing over a couple of different examples. We'll look at one question where it's like kind of harder that we'll need to do a diagram to help us represent, but we'll get to it. So I want you to try to come up with these ones on your own. There's two questions. So a survey of pet owners, or in a survey of pet owners, 45% of the people said they own a dog. 27% of people said they own a cat. And then 12% of people said they own both a dog and a cat, at least. So we want to find what is the probability that a dog owner also owns a cat. So for what's the probability that this person owns a cat given that they already own a dog? So take a moment, see if you can figure out what are my pieces I need.
Isn't it like one that overlaps?
So it's always the overlap of the two, probability of both occurring, divided by the probability of that given event. So find what's that overlap and what's that given event. See if you can find those two. So once again, we're always looking at the probability of both divided by that probability of the given. Divided by that 5. That's second piece. So what was my probability of both? My probability is my dog. Be 45. If we divide those two, we should get 27%, I think. That's my probability of owning a cat, given that the person, or that's how many cat owners there are out of our group of dog owners. 27% of all of our dog owners are actually also cat owners. Now we want to see, is this the same thing if I switch it around? Is it the same if I do a probability of a dog given that I have a cat? Sorry, I'm just doing all kinds of stuff. So probability of a dog given that I have a cat, or that I have a cat. How is this different, Morgan?
Because instead of putting it over the probability of the dog, it's put on the cat.
Okay, so it's still going to be that 12 on top, still going to be the probability of both. But instead of putting it over the probability of the dog, which was the 45, I have to put it over the probability of the cat, which is 27. And so if we divide that, we only get 0.44. And so flipping these events around will get you different answers. The only time they will ever be the same is if the probability of owning a dog and the probability of owning a cat are equal. That's the only time they should be the same. But if the probability of them are different, like what we had here, 45 and 27, you'll get different results. Are we okay with this? A little more comfortable? I'm going to skip this last one and we'll come back to it. Okay. So conditional probability if your two events are independent. If I flip a coin, is that coin flip going to change if I know my dice already landed on a 6? So flipping a coin and rolling a dice are independent events. Will my probability of flipping my coin, will that change if I already know my dice is a 6? So my probability of getting a heads, given that I already know I got a 6, doesn't change. It's still going to be a 50-50 chance of getting a heads. So for independent events, the probability of a given statement or probability of a conditional probability of this given that, it doesn't matter what the second event is. It's not affecting it. And so it's still just going to be the probability of that first event. Does that make sense? So the probability of drawing a diamond from a deck of cards, given that you rolled a 4 on a standard dice, is still the same probability of just drawing a diamond from a deck of cards. It's still going to be 1 in 4 options. It doesn't matter what number I rolled on that dice because it doesn't affect my probability. Are we okay with that? Independent events should not affect each other, so conditional probability should not be changed based on an independent. Alright, now let's talk about this last one. Sometimes with these questions, they might give you a lot of information, and it might be hard to figure out what you're actually looking for. So let's just look at this example. So a college reported that the following based off their graduation data. So they looked at all of this graduation data over the past couple of years, and this is what they found. So 70% of the freshmen who attended this college attended a public school before coming to college. 60% of the freshmen who attended a public school graduated within 5 years. So 60% of those public school students graduated within 5 years. And then 80% of the freshmen who did not attend a public school, of that other group who did not go to public school, 80% of them graduated the college within 5 years. We want to try to figure out what is the total percentage of all of the freshmen who graduated within 5 years. What is that total percentage? It's just a random freshman. What's your probability of graduating within 5 years? It doesn't matter if you're public school or private school. So they give us a lot of information to sort of piece through this. And so with something like this, it's probably easiest just to break it down to a little bit. So let's start breaking it down into possibilities or groups. So I know the first possibility is public school or not. So a student could go to public school, or they could go to some other school. Those are the two options I'm looking at right now. Doesn't matter what that other school is. What's my probability of going to public school? 70% of our students, at 0.7. Based on that, what's my probability of going to another type of school? 0.3. So 70% of the students went to a private school, so the other 30% of students went to some other type of school. So we have to remember that together these need to equal 100%. And so that's where we get the 0.3 from. If 70% went here, the other 30% had to go somewhere else. Now, after we sort of sorted through this, we know that these students either graduated or did not. They either graduated within 5 years, or they didn't graduate, or it took longer than 5 years. Okay. My public school students. How many public school students graduated within 5 years? 60%. Based off of that, how many of them did not? 40%. My other students, other school, how many of them graduated within 5 years? 80%, and how many of them did not? 20. So we're looking at the percentage of all of the students who graduated within 5 years. So we went this group right here, and this group right here. We have to find both those probabilities of being in one of those two groups, and that will be our probability of all of them. How can I find the probability of being a public school student and graduating within 5 years? How many of my students went to public school? And how many of those students graduated within 5 years? So if we sort of think about it as like a big group, 70% of these students went to public school. And of that 70%, 60% of these students graduated within 5 years. So we have to figure out how much of my pie is that piece. So it's 60% of 70%. So in order to find what 60% of 70% is, we just take 70%, multiply by 60%, and now give us a percentage. And so we multiply these two together, so 0.42. So that is my percentage of being a public school student and graduating within 5 years. That and between them. Are we okay with that? What was that? So if you're trying to find a percentage, if I want to find the percentage of, let's get an example. If I have a class of 30, and I want to figure out what is 50% of that class, I multiply the two. I take 50% times 30, and that gives me my amount. So if I have 70%, and I want to find what 60% of 70% is, I take 70%, multiply by 60%, and that's my percent of my percent. It's just a little weird because we're finding the percentage of a percentage rather than finding it out of a total number. But you can think about it as like, pretend I have 70 students, I want to find 60% of that 70, it's 42. That's another thing. So that's one group. I still have another group. I still have my other students who graduated within 5 years. So if I have 30% of them are other students of my total, and then 80% of my other students graduated within 5 years, it'd be 0.3 times 0.8, my 30% times my 80%, which is 0.24. So 24% of my entire population of students went to public or went to another school and graduated within 5 years. It is, yeah. And so my entire graduating percentage will be my 42 and my 24 put together. So a total of 0.66, or 66% of all of my students should graduate within 5 years. So sometimes, if you encounter a lot of information, it might be helpful just to sort of break it down. What are my options? Heads or tails? 1, 2, 3, 4, 5, or 6. Like, what are my options? And then write down what's my probability of getting heads? What's my probability of getting tails? What's my probability of owning a cat? What's my probability of owning a dog? And sort of break through those options. And then use those, and then multiplying down. You just multiply your way down to find each of the probabilities. If I want to find the probability of being a public school student and not graduating, it would just be 0.7. And that can give you each of the probabilities, and then figure out, okay, what categories do I want? Which are the correct answers? This one is correct, that one's correct, that one's correct, and then just add those results together. So anytime you see a really, really tough problem like that, it might just be easier to sort of break it down if it's possible, those situations. Always remember, though, that if the probability of this occurring, the probability of it not occurring is just -1, or 1 minus whatever you have. You just take that rest of that 100%. Are we okay with this? So once again, tomorrow we're going to practice a little bit. Wednesday will be more of a review day. I'm going to try to sort of, your class is a little different. I'm going to try to split up the groups into students who might need a little bit more practice compared to students who feel a little bit more comfortable and feel a little bit more independent. I'll work with the ones who need a little bit more practice. But with your classes, because you're just small, it might be a little different. And then Thursday, once again, we'll take a quick, brief moment to review, and then that'll be your probability assessment. That'll be your last grade on this 9 weeks. Any other questions, concerns, comments, statements?
Next
Next Tuesday.
Oh, yay.
Next